All right, so in this video, I want us to start looking at titrations, which you may be familiar with from Chem 161, but this time with a little bit more of that 163 flair. So just as a reminder on what titrations are, kind of how we tend to see them, right? Titrations are just a method used to determine usually like an unknown concentration by reacting it with a precise amount of a known solution. Generally, we'll see titrations in the case of like acid-base neutralizations, but they can be all sorts of different reactions. For instance, there are redox titrations, titrations in which you produce like a solid, right? So a precipitation reaction, for instance. But in a lot of scenarios, right, we will see the acid-base titration as kind of like the quintessential way to, again, determine an unknown concentration from a known one. Generally speaking, in an acid-base titration, we have like some acid sample in our flask, and then we have some strong base being used as the titrant, so as the stuff that is in the burette. And so in Chem 161, what you were trying to do often with the titrations was like get to just the right amount of your titrant being added to your acid solution. This was known as the equivalence point. This is the point at which the moles of H plus that were initially in the flask from the acid, those are being neutralized by the same number of moles of OH minus being added by the base, right? And so that equivalence point is when you have that perfect neutralization. And we saw that with like a color change, right? As soon as a little bit of excess base gets into the mixture, right, it then changes color to that like magenta or hopefully just like a faint pink color. Now, what we didn't really get into in Chem 161 was how actually that neutralization does not necessarily give us just like a perfectly neutral solution. If we have, say, a strong acid reacting with a strong base, then at the equivalence point, we do in fact have just like a perfectly neutral pH. So if I were to measure the pH at my equivalence point for a strong acid, strong base titration, I would see a pH equal to 7. But imagine instead if I had like a strong base being added to a weak acid. So with that weak acid, right, do we think that the resulting solution is going to have a pH that is greater than or less than 7, right? What do we think the pH would be at that equivalence point in a weak acid with a strong base titration? You can pause, kind of ponder on this, and then we can go over the answer in just a moment. So when we have a weak acid neutralized by a strong base, what we're basically making there is, for one, like water, right, from our neutralization, but then we're also making like an ionic compound, right? You guys learned about kind of the double displacement reactions or double replacement reactions from Chem 161. That same reaction is occurring right here with this neutralization. However, right, when you have a weak acid paired with a strong base, basically the cation of the strong base, that's going to pair up with the anion of the weak acid and then make some ionic compound from that. Now, as we learned about in chapter 16, when you have an ionic compound, the ions themselves can correspond with either a weak acid or a strong base. And so if you have, this salt described right here, this is a salt with an anion from a weak acid and a cation from a strong base. That's going to give you then some overall basic solution as a result there. And so the pH at the equivalence point for these types of titrations will actually be greater than 7. I have here an illustration of actually the pH of an entire titration for a weak acid neutralized by a strong base, in this case sodium hydroxide, and that's shown on this line here in black. Now this actually maps out not just the pH leading up to the equivalence point, but even beyond that. So there are certain parts of this curve here that I want to point out and mention, but right on the y-axis of this curve is the pH, on the x-axis is the volume of base being added to it. And so initially, before we've added any base, right, we have just like our plain weak acid in solution. But as we add hydroxide to that, right, that's going to neutralize some of the weak acid, make its conjugate base then, and then eventually once we reach that equivalence point, essentially all of the acid has been neutralized, so all of the acid has dissociated, and then after that point, we're just adding in excess base into there. So these little pictures map out those different kind of regions of the curve, right? It shows how our initial state compares to our final state after we have all of this excess hydroxide around. But that just gives you kind of a visual as to like what is going on in this mixture as this titration progresses. Because previously we were kind of just only concerned with the titration, say, at the equivalence point. We didn't think about much of the in-between of that. Now, speaking of in-between, the pure like in-between of the initial 0 milliliters being added and the equivalence point being added, this is known as the midpoint, or sometimes called the half equivalence point. The midpoint is literally halfway to the equivalence point in terms of volume being added. So this represents when we have half of our acid neutralized, meaning that we still have some acid around, but we also just have the same amount of its conjugate base that was produced from that through that neutralization step. Now, the midpoint is kind of special because that concentration of the weak acid and conjugate base are the same. This means then that at the midpoint, the pH of the solution is going to be equal to the pKa. This relates back to the Henderson-Hasselbalch equation and buffers, right? Within this range where the concentration of the acid and its conjugate base are kind of similar to one another, we can apply the Henderson-Hasselbalch equation. And if specifically the acid and conjugate base concentrations are entirely the same, then that means that the like plus log whatever part of the Hendy-Haas equation, that just becomes 0. So that's why at the midpoint, pH is exactly equal to pKa. So we can see that here in this titration curve, as it's called. This just maps out the pH across the titration. So we can see kind of how the pH is increasing as we add sodium hydroxide, but how that increase is not really linear, right? I mean, for one, pH is a logarithmic scale, so we wouldn't necessarily expect it to be like a straight line. But like beyond that, right, because we have kind of this area where our weak acid is just partially neutralized, right, giving us some of its conjugate base, we're essentially making a buffer as we do a titration. Now, we'll get into a lot of examples in class on kind of different calculations that we can make involving titrations. It's very similar to like the neutralizations that we saw in like the buffers video, right, kind of how we can reason through finding the pH at these different points in a titration. But for now, I want us to just continue to think a little bit more conceptually and take a look at, some other titration curves kind of similar to this and see how they compare. So we can consider also maybe titrations that are not necessarily like a strong base being added to a weak acid or even a strong acid. Instead, right, you could have, say, a titration where acid is being added from the burette to the base in the flask. And so you can kind of imagine what that would look like, right? I have right here a titration curve of a weak base, ammonia, being titrated with hydrochloric acid, a strong acid. And so kind of the way that this looks is essentially flipped from what we saw before. It's like a mirror image of it. You start with a high pH because you have just like your pure base in solution. And then as you continue to add hydrochloric acid to that, the pH lowers, but still we see like some important areas noted here, right? For one, we have the equivalence point, again, where we have like equal amounts of acid being added to base. Then halfway to that is the midpoint. Again, that area around the midpoint where we have, say, similar amounts of our weak base and conjugate acid, this is referred to as the buffer region. This is the area which we can use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation may look a little bit different or just need some extra steps in it when we are considering a base dissociation instead, right? The Henderson-Hasselbalch equation is, involving things like pKa, so an acid dissociation constant. Typically for a base, you're not given a Ka, right? You're given a Kb, and so you may need to do some additional steps in the math with that. But again, the kind of picture of this titration curve is very similar to what we saw in the first one, where we still have this like gradual decrease in pH just kind of as we continue to add acid to it. Eventually, after the equivalence point, we're just adding in excess acid, and so you can see from the pictures right here that once all of the NH3 has been neutralized, right, you're just adding in then excess acid, and so you'll just have more hydronium then as you continue to add hydrochloric acid to the mixture. Now lastly, I want us to consider even more complicated titrations, for instance those which may have like polyprotic acids featured. So that's what's drawn out right here. So I have the titration curve of sulfurous acid, or H2SO3, being neutralized with sodium hydroxide, and sort of the way that this looks is very similar to just the strong base with a weak acid titration from before, but it kind of looks as if I took two of those titration curves and I just had them happening like in sequence with one another. So maybe looking at like the first half of this graph, right, going from say 0 to 60 milliliters of sodium hydroxide, right, you can see again, you've got like an equivalence point at this sort of steep point in the curve. You have halfway to that the midpoint, and then around the midpoint is the buffer region. At 60 milliliters, we see essentially the same thing happen again, right? We have, again, like a slow increase in that buffer region, and then at 80 milliliters, that's where there's a second equivalence point. Now, the reason that we have these two equivalence points and these two midpoints is because remember that when you have a polyprotic acid, it's like you have basically two acids, two protons coming off in sequence with one another. So the first midpoint and the first equivalence point, those are just really thinking about the first proton leaving. The second equivalence point at the very end and the second midpoint getting there, right, that's going to correspond with the second proton leaving. Now, it can be a little confusing, especially if we don't have the picture laid out right in front of us, is that while before we thought of the midpoint as like literally just the one half of the equivalence point, that doesn't totally work when we have polyprotic acids. For instance, like the second equivalence point is at 80 milliliters of sodium hydroxide. The second midpoint is only at 60 milliliters, so that's not one half of 80. But right, how we kind of calculate it is just in terms of right each step individually. So the first step, getting to that first equivalence point, that was 40 milliliters, and so the midpoint for that first part is just one half of that, 20. Then for the second step, right, although that goes up to 80 milliliters as the second equivalence point, we're going to say that that's starting from the 40 of our first equivalence point. And so halfway between that, that's our second midpoint. So that's why we have kind of these sequential midpoints and equivalence points spread out like so. It's not like a perfect just one half for the midpoint every time, or you do have to kind of think about it in context, especially if you have a polyprotic acid. Now, as far as these different midpoints go, right, again, the midpoint is helpful because it tells us that the pH is equal to the pKa. Remember that in polyprotic acids, you have multiple Ka values, so Ka1, Ka2. Within our titration curve, pKa1 matches with the pH at the first midpoint. pKa2 matches with the pH at the second midpoint. So again, we see still those same relationships between pH and pKa, and because in a polyprotic acid you have multiple Kas, that's where these multiple midpoints kind of come into play. Now again, we'll get into more of the harder calculations involving titrations, but here I just want to go over a few examples, finding specific points in a titration curve. So say here I have a titration where I have 20 milliliters of 1 molar sodium carbonate, or Na2CO3. This is being titrated with 1 molar hydrochloric acid. So my question here, or I have a few questions actually, but the first one is how many milliliters of hydrochloric acid will be needed to reach the first equivalence point in this titration? So remember that with that first equivalence point, we're really just talking about like one equivalent of H plus being reacted with this weak base. So right when we're calculating this, we don't necessarily need to worry about molar coefficients or anything, right? It is truly just like a 1-to-1 ratio of our acid to base here. All right, so finding our first equivalence point for this titration is going to be pretty simple, honestly. It's like ridiculously easy to find the equivalence point. But so what I've got as my equivalence point here was 20.00 milliliters. To prove how we can do this, right, I first begin by thinking about just what reaction is occurring here. And right, I have basically carbonate from the sodium carbonate reacting with H plus from the HCl to form then its conjugate acid, HCO3 minus, or bicarbonate. Because again, this is just one step in the protonation, I'm not going to fully reprotonate the carbonate into, say, carbonic acid, right? So we're only adding one proton at a time here. And because of that, that gives us just all 1-to-1 molar ratios of our products and reactants. And so if I want to find out exactly how much of the hydrochloric acid in terms of volume are needed to meet this first neutralization, I'm basically just going to employ, again, the M1V1 equals M2V2 equation that I have right here. So I know in Chem 161, you're always warned to like not use M1V1 for titrations, and that's true for 161, but here, because we have all just 1-to-1 molar coefficients, we can use M1V1, and it's actually super easy for us to do so. It gives us then the volume for that first equivalence point as 20.0 milliliters. So right, finding our first equivalence point is super duper easy just using that equation. But what if instead I asked you for the volume to reach, say, the first midpoint? How many milliliters would that be? Hopefully you're thinking, okay, the midpoint is 1/2 of the equivalence point. So 1/2 of 20 is 10 milliliters for that first midpoint. Or what if instead we wanted to reach the second equivalence point? How many milliliters would be required to do that? So for our second equivalence point, because it is just like basically doing the titration once more, right? We already know that for the first equivalence point, it takes 20 milliliters. If we want to reach the second equivalence point, we're just going to do another 20 milliliters, so 40 ml in this case. And if I wanted to reach the second midpoint, again, the midpoint here is not necessarily just 1/2 of the second equivalence point, it's halfway between our equivalence points. So halfway between 20 for the first equivalence point, 40 for the second equivalence point. The second midpoint is going to be then 30 milliliters. So these calculations for finding out just like where in the titration curve we're talking about, these are very simple. For the actual determination of like the pH at these different points, that's going to be a little bit more involved, but we'll follow up with that in class and kind of discuss, how we can predict the pH at different points in a titration based off of that. But right, this is just like a brief introduction to titrations. Please let me know if you have any questions, and I'm always happy to help. Bye.